Okay. So yesterday we looked at the power rule, and we were looking about what happens when we differentiate an x to the n. And we get something times x to the n minus 1. And now if you think about that, that should be kind of make sense to you, right? Because if you're just thinking in terms of units, rise over run is like x to the n. The units on the bottom is x. So you've got like x to the n minus 1, x to the n divided by x, and that's why you get x to the n minus 1 there. So when you get a power, it's kind of natural that when you take the derivative, you're going to remove 1 from the power. Okay, so today we want to have a look at the exponential. An exponential is different from a power, right? Because at addition, the variable is in the base and the exponent is fixed. With an exponential, it's the other way around. The base is fixed and the variable is in the exponent. And we kind of already know what the answer is going to be. Okay, so if we look at the graph of an exponential, it's sort of going to go like that. We see that, well, what's the slope like? Well, the slope is going to be positive because it's increasing. The second derivative is going to be positive because it's concave up. It's going to start out small back here because it's flat, and then it's going to get steeper and steeper as we go along. So we're going to expect the derivative to kind of look like the function itself. So there's no diminution in the power, okay? And also we know what is the defining thing about exponential. Exponentials have constant relative growth. Right, so exponentials grow at like 5% per year, or they decay at 10% per year. There's like this fixed thing. So that means what's the relative rate of growth? It's y prime on y. So the derivative divided by the quantity itself should be a constant. Okay, and let's do some algebra on that. There's only one thing to do, right? Y prime equals ky. And so we see that the derivative is going to be proportional to itself. Okay, that makes sense, that the rate of change is proportional to itself. So like if you put money in the bank, how much it changes depends upon how much money you put in. When you've got a population growing, how many babies are born depends upon how big the population is. Like the bigger the population, the more babies born. The more money you have in the bank, the more money you get in interest. The more of a radioactive element you have, the more of it that decays. So it depends upon how much there is. Okay, so we're going great. Yeah, okay, we're just without even really doing anything, we've already kind of figured out what's going to happen. So let's actually try and figure out what is precisely happening. So the big thing is, well, what is that k right there? And for that, we have to do some actual real math. Okay, so how do we do the derivative? Well, we want to do a rise over run. Okay, so let's do that. So we get a to the x plus h minus a to the a x minus h over 2h, for instance. That's how I ask this kind of question to you in a homework question, like, what was the derivative of, was it 5 to the x and x equals 2 or something like that. So you would have done exactly that. Okay, so let's do a bit of algebra. Now here the algebra is a little bit less clear what we're going to do, but there's really not much we can do. So we can use the exponent rule, right? So a to the x plus h equals a to the x times a to the h. And a to the x minus h equals a to the x times a to the minus h on 2h. So nothing startling there. What can we do next? There's really only one bit of algebra to do. What's that? Sorry? Oh, we could sorry, there are two things. Okay, we're not going to do that. What's the other algebra kind of thing we can do whenever you see something like this? Like if I have 2x minus 5x, what do? You can put the x's together, right? Here I've got a to the x. I can put them together. I can sort of pull that out as a common factor. So I've got a to the x times a to the h minus a to the minus h over 2h. That's just rewriting it. Okay? We're good now. Because what did we want to do? We wanted to figure out what the constant was that we multiplied the function by. And so here we have the function. And do you see that this is a constant? Because there's no x in there. Remember, h is just some really, really small number. We make it smaller and smaller and smaller. So this equals the derivative at 0. So this tells us that y prime equals y prime at 0 times y. So the slope at 0 is exactly the constant of proportionality. Yeah, that was a bit fancy, but that's kind of knowable. Okay.
So that works for any exponential function?
Any exponential function will, right? That's why I made the a, anything that a could be anything. So it's a parameter. It's constant for this thing, but for different a's. But let's go ahead and actually try some of that. Daily taking our life into our hands. My hands are too big. Good thing about the chain is it doesn't slip. Okay. Let's share. Oops, I should turn that on. Okay, so here's a little Excel file I dreamt up for us to show the exponential. So what I've done, I've just done the typical kind of grid of points here, and here's the function, and here I put in the base. So this is allowing us to figure out what the base is. And here's my slope. I'm just doing rise over run. I'm centered at 0. That's what we want. We want to know what the slope is at 0. Now, 0.75 is approximately the answer, but we can see that it's not going to be a good answer, right? Because we can still see a curve here. So let's make our window smaller. So let's make it like 0.2 maybe. Oh, that's kind of better. And maybe we'll just do zoom in once more. Okay, that looks pretty good. Okay, so let's make a table now. So when the base is 2, the derivative at 0 is 0.693. Okay, nothing. So now I'm going to replace the base by 3. What do you think is going to happen to this number? Is it going to go up or is it going to go down? Is it going to be steeper or is it going to be shallower? Going from 2 to the x to 3 to the x, which is going to grow faster, 3 to the x or 2 to the x? 3 to the x is going to grow faster. So expect when the base is 3 to the slope to be steeper. So let's see what happens. Oh. 1.0, was it 97? Just doing it. Okay, so this is telling us, right, that the derivative of 2 to the x is 0.693 times 2 to the x. The derivative of 3 to the x is 1.097 times 3 to the x. Now, somewhere in between 2 and 3 is going to be a derivative, a base, such that its derivative at 0 is going to be 1. And for such a function, the derivative of it is going to be itself. Okay, so let's try and figure that out. So maybe we'll try 2.7. Oh, pretty close, right? 2.7 is 1 point, what is it? Oh no, it's 0.993. Okay, so we make the base a little bit bigger, so maybe 2.71, for instance. So now it's 0.997. Does anyone know where we're ending up? We're going to end up at 1, but what base is going to give us 1? Does anyone recognize this number? 2.71. It's E, exactly right. So let's over here put E. So let's put equals. X is how you do E. So this is E to the 1, which is E. Oh, that's just, it should have been 1. That's just some numerical error. But yeah. If the base is E, the derivative is 1, and that tells us that the derivative of E to the x is E to the x. And actually, we'll use this as there's the actual definition of E. It's the base whose derivative gives us a slope of 1 at the origin when x is 0. And this is why we use e to the x, right? Because it has this nice derivative property. And that's why we use e to the x rather than 10 to the x or 2 to the x or whatever. Is that? Huh. Okay. So let's put in a blank here. So we've got the power rule, which is that the exponential x to the n, the derivative of x to the n is n times x to the n minus 1. We've got the exponential rule. Says the derivative of e to the x is e to the x. What about the derivative of e to the kx? Well, that turns out to be k times e to the kx. So again, right, it's the derivative is going to be proportional to itself. So the e to the kx always goes there. Here's the constant of proportionality. It turns out that's the same k as there. And the reason for that is, well, think about what you're doing when you're doing x times k and then exponentially. You're making the horizontal go k times quicker. So you're going faster there, so that when you do your rise over run, you're making this happen quicker. You just think of it as speed. You're multiplying the speed by k, so that means you're going to get this way k times faster. So it's going to look like this. It's going to have the same rise, but this run is 1/k of there. So you're just multiplying the speed by k. I'll make that more stricter when we come to something called the chain rule later, but that's always sort of the case. Okay. Well, what's the derivative of a to the x then? Well, let's think about it in terms of e. A to the x is equal e to the kx for some k. We can figure out what k is by taking logs. So x ln a equals kx. Right, just by taking logs, right, down comes the exponent. That tells us that k equals ln of a. So this equals e to the ln a times x. So when we take the derivative of this, we get ln of a times e to the ln ln ax, and that's just ln of a times a to the x. Okay, so let's just get rid of all that reasoning then. The only thing you have to know is that equals ln of a times a to the x. Does anyone know what ln of 2 is? It's 0.693, like we saw. The ln of 3 is like 1.09, like we saw before. So these are some nice rules that you should just store away somewhere. These ones definitely you should know by heart. This one, maybe. Okay, so now we can start doing really complicated derivatives. All right, so we can do, for example, 5 plus 3x squared plus 2 times 3x plus e to the 2x plus 5 e to the x. Okay, just a whole bunch of symbols, but it's easy to differentiate because it's a sum, so we just do each one term by term. The derivative of 5 is 0. It's a constant, right? Derivative of 3x squared. So the derivative of x squared. Down comes the power. And we subtract 1 from the power. What's that?
X.
It's x, but what happens to the 2? The derivative of x squared is 2x. Right, down comes the power. So 2x times 3, it's 6x. Right, because this constant is multiplying it. So it's going to be 3 times the derivative of x squared. Then we get 2 times, well, the derivative of this is going to be ln of 3 times 3x. The derivative of e to the 2x is 2e to the 2x. And the derivative of e to the x is e to the x. Okay, so that we did every rule that we had so far. People comfortable with that? Anyone want to make a comment? Okay, so we've done the derivatives of exponentials. What comes next? We differentiate exponentials. What else do we want to differentiate? What's kind of paired with exponentials? Logarithms. So we need a logarithm rule. What could possibly be the derivative? So we want to know, what is the derivative of ln of x? Okay. Well, let's think. So what we're going to use is the fact that logarithms is the inverse of exponentials. So here is e to the x. Okay, so here is a point. A, so this is the point A, e to the A. And we look at the little triangle here. What is the slope of this triangle? What is the slope here? So what's the derivative of e to the x at A? Well, for a start, what is the derivative of e to the x? E to the x. We're at A, so what is the slope? E to the A. Right, because x equals A, so if the derivative is e to the x, the derivative, the slope is e to the A, which is the y value. Right there. So at each point along this graph, the slope is the y value. How do we get inverse functions? We just flip it over, right? We swap x and y. That's how you get inverse functions. So ln of x kind of looks like this. We get it by taking the mirror image of e to the x. Okay, so this point here is the point e to the A. Okay. Or we would call it maybe B ln of B. The same thing. Right, the inverse of each other, this is what it means to be an inverse. So again, let's have a look at the same, at this triangle, it gets flipped over. So it gets the mirror image of that triangle. So it's like here. So if the slope of this is y, the slope of this is 1 over y. Right, because it's mirrored, but y and x have been swapped. Right, so 1 over y, the y here is the x here. So the slope of this is 1 over x. I'm not expecting you to repeat this, but this is the reason why. I just didn't want to write this down without giving any possible explanation. But because the derivative of the exponential is the y value, the derivative of the logarithm is 1 over the x value, just because of that mirroring. But this is the thing you've got to remember. That the derivative of ln of x is 1 on x. Okay, so now we can differentiate more things. So, for example, 5 ln of x plus e to the x plus square root of x. What's the derivative of this piece? Derivative of ln of x is 1 over x. And what happens to the 5? It stays there. Okay, because it's a constant multiple. The derivative of e to the x? Just e to the x. Derivative of x square root of x, well that's x to the 1/2. So we add 1/2 x to the minus 1/2. the derivative of ln of x plus 1 on x. Okay, derivative of ln of x, 1 over x. 1 over derivative of 1 over x, well, 1 over x is the same thing as x to the minus 1. So down comes the power. We get minus 1. We subtract 1 from the power. So it's 1 on x minus 1 on x squared is the derivative. Okay, so what does this mean? This means we've now just got a whole bunch of other stuff we can, whole bunch of other problems we can solve. So for example, Nevada's population is given by P of t equals 2.020 times 1.036 to the t, where t is years since year 2000 and p is in millions. Okay, we've got a formula, so we can answer questions about it. And so, for example, what is rate of change in 2020? I'm asking for the rate of change, so what do we got to do to this formula? We've got to take the derivative of it. Okay, so P dash of t. This is a constant multiple, so it stays. 2.020. This is an exponential, so it's in its derivative, the exponential stays. And what do we multiply here by? The log of the base. Okay, so we have now that we have a formula for the rate of change. We want to find the rate of change in 2020. So what value do we plug in for t? 20. So the rate of change equals 2.020 times ln of 1.036 times 1.036 to 20. What's the units?
Population per year.
And what's the population measured in? Millions. Okay. So if you didn't have a calculator, this is as far as you can get. But of course, if you had a calculator, you would just plug these numbers in here and get an answer. Has anyone got a calculator?
.145.
0.145. Okay, so if that's millions, 0.145 is 145,000. 145,000 people a year. So that's what the model says that Nevada's population is growing by. Okay, does that make sense? What another type of question? Find the tangent line of y equals ln of x at x equals 2. That's a standard kind of question I ask. How do we find a tangent line? We need a point and a slope. So the point is x is 2. What is y? ln of 2. And the slope is? What's the derivative of ln of x? Plug in 2. 1/2. Okay, and so then we just do y minus ln of 2 equals 1/2 x minus 2. And so if you want to tie it up again, get y equals x1, 2, so it's minus 1 plus ln of 2 minus 1. So there's the slope and there's the y-intercept. So what does ln of 2.1 approximately equal? Well, it's going to equal ln of 2 plus 0.1 times the slope. The slope is 1/2. Right, so it's approximately going to be ln of 2 plus 0.05. So ln of 2 is 0.693, ln of 2.1 is going to be 0.743 approximately. Okay, so that's a frequent question I ask, is use the tangent line to make approximations. So you should all be super comfortable with those. Another question, okay? Another situation where exponentials come up a lot is interest rates. So let's say we save $1,000 at 3% interest. So that means our money then is going to have, oh, when I give interest rate, what else do I have to say about it? Right, so let's say compounded continuously. Right, so then the formula is 1,000 times e to the 0.03 t. This is too easy, right? Because the base is e, so we can take its derivative straightforwardly. F prime of t then is, down comes the 0.03. We multiply it by 1,000, we get 30, I think. Okay. We can figure out what those quantities is by putting it in the calculator. But what do these quantities mean? What does f of 10 tell us? Right, so if we put it more in practical terms, what the y value is how much money we have saved in 10 years. Okay? What does f prime of 10 tell us? Right, so it's the rate at which we're earning. So a marginal thing would be, you know, how much money we earn in that 10th year. Approximately. It's kind of like the marginal earnings that we have, our marginal rate. Okay, so we have formulas and we have our situation. So you have to be able to do your math, to do the formulas, and then you have to have some common sense to be, or whatever, like you have to think about what things mean to interpret what it is to put things in terms of words. What if instead of saying compounded continuously, I said compounded annually? How does that change things? Right, so instead of e to the 0.03t, we would put 1.03 to the t. And then this would change to 1,000 times ln of 1.03 times 1.03 to t. But that's just the math difference, right? And of course, we know that this would mean these quantities would be a little bit below the e to the 3t, just because compounding continuously gives you more money than compounding annually. Okay. Try this again. Hannah, here's a question for you. So here is in the blue, dark blue here is, oh, let me turn the light up so it's easier to see. Oops. No, it doesn't really matter, does it? Okay, do you see that line? So that's our exponential function ATX. And below it, shadowing it is its derivative. So we can see that it's a constant times a to the x. Which one of these answers do you think is correct? What do you think what would be a possibility for the base A? So the hint I'll give you is, remember that the derivative of a to the x is some constant times a to the x. So in this case here, what can you tell me about the constant? Is it bigger than 1 or less than 1? Right, because f prime of x is smaller than f of x. So how much is it being scaled by?
I can see f prime of x.
I
That's
have
no idea what you're talking about because I can't see f prime of x.
f prime of x is just right here. So f prime of x is less than f of x. So what does that tell you about k?
Like it's smaller.
It's smaller. It has to be smaller than 1, right? If it was equal to 1, then f prime of x would equal f of x, and the base would have to be e. But it's smaller than that. So which one of these? So what happens if the base was 1? What would the curve look like? So what does 1 to the x look like? It just looks like 1, right? It's just 1 all the time. So it can't be that. What's the difference between the constants between this number and these two numbers? Because remember, k has to equal ln of a. So do you remember which numbers, when we did it on the calculator, we looked at ln of 2 and ln of 3? Remember which one was less than 1? Yeah. So ln of 2 is 0.69, right? So the answer to this was B, because 2 to the x, its derivative lies below it. 3 to the x and 4 to the x, the derivatives lie above it. And so the answer was actually B. Okay. Anyway, that was just a little thing to think about. Okay, and we'll see you later. Bye, Phoebe.